Welcome to springlib.
This problem, we're going to use the molecular orbital diagram given to predict which species in each pair has a stronger bond. So for both the fluorine and oxygen, we're going to be using this molecular orbital diagram. So the sigma bonding for the 2p orbitals is going to be lower in energy than the pi bonding molecular orbital. So let's do the fluorine first. So looking at the periodic table, there are 5 p electrons in the 2p orbitals. The 2s is completely filled, so we're going to go ahead and fill this in. And then each of the fluorines will contribute 5 from the 2p. So we're going to fill in a total of 10 into the molecular orbitals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we can calculate the bond order. So that's going to be number of electrons in bonding minus number of electrons in antibonding divided by 2. There are 8 in the bonding, and then there are 6 in the antibonding. That's 2 divided by 2. That gives us a bond order of 1. It makes sense because there's a single bond between the 2 fluorine atoms in diatomic fluorine. So then we have F2 negative. So we're just adding one more electron. So there will be one more antibonding electron. Calculating our bond order. The antibonding electrons are now equal to 7. So we have 1 divided by 2. The bond order is therefore 1/2. The stronger bond is an F2. The higher the bond order, the stronger the bond. So then we'll do O2 negative and O2 positive. So first let's start with O2 negative. So look on the periodic table and we see that there are 4 p electrons contributed from each of the oxygen atoms. So that's what this is going to look like. And then we'll have one more electron. So we're just going to add one more electron to one of the atomic orbitals. So the 2s is completely filled, and then we'll just look at the 2p. So we have a total of 9 electrons. So what we need to do is we only have 3 in the pi antibonding. So now let's calculate the bond order. So we need to find the number in the bonding orbitals. So that's 8. In the antibonding, we look at the ones in the pi antibonding from the 2p. So there's 3 in there, and there's 2 in the sigma antibonding from the 2s. So that's 5. So we do 8 minus 5 divided by 2. That gives you 3/2. It's 1.5. So then for the next one, it's O2 positive. So instead of adding one electron, like we did for O2 negative, we have to take away one electron. So we're just going to take one of these away. So we know we will need to take 2 of the electrons away from the molecular orbital diagram for O2 negative. We took away 2 from the antibonding. So we have 3 in the antibonding now. So we get 2.5. So therefore we know that since the bond order for O2 positive is going to be 2.5, which is higher than the one for O2 negative, then O2 positive has the stronger bond. Okay, so now for the last one. For the last one, we have to switch the pi and sigma bonding orbitals for the 2p. So the pi will just be on the bottom here, and the sigma will be up there. Okay, so then looking at the periodic table, we see that there are two 2p electrons for carbons. So each of the carbon atoms will contribute 2. So we have C2 and C2, 2 plus. So let's just do C2 first. So the 2s is completely filled, and we need to fill in 4 into the 2p molecular orbitals. Then let's calculate the bond order. So we do bonding minus number of anti-bonding divided by 2. So that's 4 divided by 2 gives us 2. And then we're just going to do C2, 2 plus. So for 2 plus, we took away 2 electrons. So let's take away 2 electrons from one of the carbon atoms, and then we'll need to take away 2 from these bonding orbitals. So now we have 4 minus 2 divided by 2. That's 2 divided by 2 is 1. So the stronger one is going to be C2 without the charge.